Hi everybody, welcome back to another day of class. I hope you're doing well and everything's is going well so far with the semester. I appreciate your feedback and I feel like um, our communication is great. I appreciate you visiting my office and contacting me through email to let me know where you're at and any updates, help that you might need. So thank you for doing that. Um, Shown on the screen right now, again, is the summary of our first project. Now, that project is scheduled to be due a week from Friday. So that would be, is it February 2nd? I believe it's due February 5th. So not the Friday, but the Monday. So February 5th, this first project is scheduled to be due. Now again, this project is a heavy project. I know it takes a lot of time. What we cover today will be kind of the last bits that you need to finish it up. And then hopefully we'll be able to have some solutions figured out. Now, throughout this class for 2900, so far to date, we've covered a few things. We've covered digitizing, georeferencing. We've covered interpolation methods and tools, among other things. So, and we've also talked about generating shape files just from tables that we may have created with Excel, for example. And today what we're going to look at is how to get kind of these final values that we need. So just looking here on the report, after interpolating our rain gauge sites, we are asked, finally report the total volume of precipitation that fell on each polygon, or in other words, each recharge area, primary recharge, secondary recharge, and primary discharge areas. The following information should be submitted in a report. So how do we get that total volume of precipitation? Now I'm going to jump back to ArcMap and we're going to see a few things that were present where we left off last time, which included our interpolation method. Okay, so we're going to look at where we left off with that and with digitizing, georeferencing, and we're going to look at how do we pull out of the polygons we have digitized, like this total volume of precipitation based off our interpolated model of precipitation values across a region. So let me jump back to ArcMap and let's just see if we can paint the picture there and then go through the process. So I'm going to minimize this. This should look somewhat familiar from what we saw on previous videos. And let me get back to where we can kind of move around the map here. Now again, just as a reminder, these are not real rain gauge sites. They are hypothetical in their well, they're made up, I should say, not even hypothetical. They were created with random numbers, but they also, just to give us an idea, they represent what we should have in terms of rain gauge data for one given year. Now keep in mind you're going to do this for 6 different years, so it's going to be a little bit of an iterative process that you'll go through to generate this information 6 times. So let's just pretend or consider this as if this is one of our years. Now, so we have the rain gauge sites. We've interpolated a raster surface based off the values at each one of those locations. And I've also created some polygons. Now I'm not showing on the map any image that has been georeferenced and consequently digitized from that georeferenced image. Rather, I just made a few polygons to represent what they might look like. Okay, so please understand that these are not based off an image, but I have polygon 1, polygon 2, and polygon 3 to represent as if you were to consider that as recharge 1, recharge 2, and primary discharge. Okay, so thinking of it as those 3 different types. Now, as you look, let's just look at polygon. Well, let's do polygon 2. Okay, so you can see the area that polygon 2 covers. Polygon 2, I'm going to zoom into it. It's kind of placed right above these mountains. And as you look at it, as I toggle it off, if this raster data set represents rainfall for each grid cell, okay, each cell of the raster, then there is a lot of rain here and not as much down here, and definitely even less right around this area. Okay, so knowing that that is, you know, how much rainfall has fallen on one little spot anywhere along this surface, but we want to know the total volume of water that has fallen over this area. So now just keep in mind, as you consider rainfall depth, if 12 inches of rain have fallen over an area in a year or some period of time, that gives you depth, right? That's one dimension. Now, if I want volume of something, I need to consider depth times by width times by length. Or I need to take that depth of water and multiply by the area that depth covers. So it would be like us taking the value of each one of these raster cells and multiplying by the cell size. Okay, which we could do to give us the volume of water on each one of those cells, and then we could sum that up. So that'll work for us if we know a few things. First, we need to know the cell size of each cell, and then we need to know the value of rainfall associated with each cell. So let's just zoom in and look at one of these cells. And as I get closer, you'll start to be able to see kind of the spatial value of each one of these. Okay, and so we have, you know, a rainfall value associated with each cell. And as I come in closer, we're not really seeing the pixels as sharply with each cell. But I wonder what the cell size is on each one of these. So something that you can do is come over to the table of contents, click on this raster. Now this is our precipitation raster, and go to properties. And inside of here, under source, we have cell size. So check this out. The cell size is 0.00757 by 0.00757. Now I wonder what units that is. Now if that's feet, 7/1000th of a foot is a pretty small quantity. So I'm guessing that we don't have our cell size in feet. In fact, I highly doubt that, knowing that we have, in terms of number of rows and columns, there's 256 columns and 251 rows, and each of them is that size. That would mean that they're not even 1 foot. Our span of precipitation data is not even 1 foot. So I'm doubting my units there, and I hope that you'll always check your units and piece together what they are. So as I consider this and look at this unit value, I'm going to think back to how this data set was created. So this precipitation data set was created based off interpolation performed on this precipitation location data set. Okay, so if you can think back to that, so let's go ahead and right click on it and let's look at the properties, see what we can piece together. And as I look at the source information for this layer, I can see that the geographic coordinate system is WGS 84, which says to me that our units are probably not in feet. Okay, angular unit degree, I'm guessing that our linear units defining the size of each cell are some fraction of a latitude and longitudinal degree, which, actually would make a lot of sense, because in 1 degree you're going to cover a lot of land on the surface of the earth. So I am guessing that our units on this raster are not what we think they are. So if we were to say, knowing these units, if we assumed they were feet and we said, well, each cell has a depth of, maybe, let me just consider one of these cells has a depth of 19 inches of water and a width of 0.007 and a length of 0.007 feet. That could give me some volume of water. It would be extremely small, and so something tells me my units are wrong. So what that unit would be if I said 19.86, okay, this number here, multiplied by the dimensions of that cell, it would be inches times degrees for a volume measurement. And that's not right. Okay, so what we need to do, we need to somehow change this raster so that the cell size is related to feet, hopefully. Couple ways that we can do that. First off, there's a tool called resample. And I just want to show you what it does. You can change the spatial resolution of a raster. So what that means is you can change the cell size. It'll grab values off of the current raster and apply it to a raster with different size cells, however you were to tell it to make those cell sizes. Okay, and looks like I clicked on the help and it's getting all mixed up on that. So the input for this tool is to put in a raster, and then you can tell it a cell size. Now notice something though, this does not have a unit associated with it, so you can't put in 100 to say, hey, make it 100 feet. It won't know that you want it in feet. It will adopt the same units of the input raster, okay, which in this case, if it's degrees, it's going to adopt cell sizes in degrees. So if we were to do it 100 by 100, we would have not even one cell. It would probably throw an error. So let me cancel out of that. What we need to do first is reproject this raster as in the coordinate system of our map. Now our map itself is in Utah State Plain Central. Okay, NAD 83, cores 96. So let's reproject this raster data set into that same system. So I'm going to come and let's find our reproject, project raster. I'm going to grab that tool. Now, so project raster, let's input our raster. It recognizes that the coordinate system of the raster is WGS 84. Our output coordinate system, I have State Plain Central, cores 96 is one of my favorites. I'm going to click OK. Let's look at the transformation that it's chosen. Now, I might want to do a little bit of research on this transformation to see how it's doing that and if that would work well for Utah. But for the sake of today's lecture, I'm going to hold off on that. Now, knowing something about State Plain Central, its linear units will be in feet, okay? And we can look at that as we consider this type of projection, linear unit US foot. And it gives it some value that's a conversion between feet and meters. I think that's great. However, I can now choose as part of the projection an output cell size. Now notice by default it says, hey, maybe 2,458 feet would be a good dimension for your cell size. I'm going to say I want 100 by 100. Okay, so I'm going to simplify that value and make it 100 by 100. And now if I choose to rename it, let's call this our, I'm going to say UT underscore central precip, just to give it a name that has significance to me, and click OK and let it crunch through that projection. Now when you project a raster, especially as you change the cell size, sometimes that takes a little bit of time. You'll see as we do larger raster grids, sometimes it really does take a while. Okay, so I'm going to close that. Let's just look at our properties here and see what we can make sense of. Okay, so this has 5,582 columns now and 6,957 rows, cell size 100 by 100. Now you might zoom into here and say, let me measure one of these cells. Is it really 100 feet? And we're going to be surprised to find, as you watch the measure tool in the upper left-hand corner, that it's not 100 feet by 100 feet. However, there are multiple cells within what it looks to be one cell. Okay, and I can click on our information tool and see that there are multiple cells that I'm selecting. Because of how the reproject worked, we lost resolution. Okay, we lost some information as we adjust the cell size. So that's a consequence of changing the cell size. Now you can see within this square that you can kind of see on all of these cells that I select, and the green dot shows the center of that cell, the value is the same. So we do have 100 by 100 foot cells on this raster grid, and I feel pretty good about that. Now this raster grid is much larger than the areas that I'm concerned about, which are polygons 1, 2, and 3. Okay, so I don't need all of this information. I need the information that's under polygons 1, 2, and 3. And let me toggle 2 back on. All the other stuff is great. It helped us get a predictable rainfall value, but I don't need it now. I need what's underneath the polygons. So I'm going to use another tool. This tool is similar to clip or extract. It's called, well, clip or intersect, I should say. It's called extract by mask. So again, I'm just going to search for this tool, extract by mask. Okay, so kind of a funny term. Let's see if we can find it. Extract by mask. I click on that, and let's see what it asks us for. This is like, if you can imagine your raster to be like your rolled out cookie dough. Okay, if you were to use a cookie cutter on cookie dough, your raster is like the dough, and a polygon is like your cookie cutter shape. And we're going to cut out pieces of the raster. So let's input our raster that we projected, Utah Central Precip, and our feature mask data, or our cookie cutter, let's make it polygon 2. Okay, so let's consider polygon 2 for right now. And I'm going to say this is our P2. I'm giving it a significant name. It's going to be saved in our geodatabase that we've already set up. I'm going to call it P2 Precip. Okay, it's our precip data under polygon 2. And I'm going to click OK and let it crunch through that. Okay, and it adds that to our table of contents. Now notice this is a piece of this raster, of our Utah Central Precipitation Value raster. This is just a little chunk of it. And if I toggle off, oops, Let me close that out. If I toggle off our polygons, you now can see that raster in and of itself, okay, has been cut out from this overall raster. Now it's pulled the same values, okay. They're colored a little bit differently because the scale has changed. Notice the scale here, the whitish colors are 29, the blackish colors are 16. Here the whitish colors were 33 and the blackish colors were 10. So the range has changed, and that's why you're seeing some discrepancy in the coloring. However, the values, it's just cut out, just like a cookie cutter in dough. Okay, so we have values of precipitation for each cell as it's been interpolated from our interpolation methods. Now, if I toggle this off, and also if I know the cell size, then we can do something with this piece of our precipitation raster, and that is we could compute the volume of water that has fallen. Because we have a depth and because we know the cell size, multiplying width of the cell by length of the cell by depth of the water should give us a volume of water. Okay, just like the length of a swimming pool times the width of a swimming pool times the depth of the water in the pool would give us the volume of water in a swimming pool. So how could we do that? How could we do some sort of operation that would come into here and multiply out those three numbers and somehow hang on to it for us? Well, let's look at that. I'm going to bring another tool in called Raster Calculator. Now, you may have used this tool earlier. Raster Calculator allows you to do algebra, map algebra, over some sort of a grid. And so we can take values in each cell and do stuff to that number. So for example, this is our P2 precip raster. I'm going to double click on it and it brings it into this box. This is kind of like our equation box or our algebraic expression box. And we can tell it to do things with the numbers in each cell of that raster. So since that value comes in as a depth of water, I'm going to multiply that value by the length of the cell and the width of the cell. So I'm going to say multiply by 100, and I can also type this in from the keyboard, times 100. So length of the cell, width of the cell. So P2 precip times 100 times 100. Now as you think about the units there, 100 is in feet, and P2 precip is in inches. Now to get inches to feet, I need to divide by 12. So I'm going to divide by 12. Now that should give us a value in cubic feet. Now if you look at the volume of water in cubic feet over an area this large, it's going to be a ginormous number, okay? And it's a valid number, but it's not the typical units that we measure volumes of water, of large quantities of water in. Usually we measure that in a unit type called acre feet. So that's like acres are like an area and feet is like a depth. And so if we could convert cubic feet to acre feet, that would be good for us. Now in 1 acre, there's 43,560 square feet. So if I take cubic feet and divide it by square feet and multiply it by 43,560 acres, okay, that should return a value. So this is just a unit conversion of acres to square feet, and so that will preserve feet in one dimension and acres in the other two dimensions, okay, in our area dimension. So this should give us a value for each cell in acre feet of water that has fallen over that area. So I'm going to say okay, and let's see what the result comes out to be. All right, it computed that quite quickly. let's just look at only that raster value. Now our range of numbers go from 0.309 to 0.573. So again, that is over a 100 foot by 100 foot square. That is the acre-feet volume of water that has fallen over that area. And just to give you kind of an idea of what 1 acre foot is, it would be like a football field. Okay, only the grass part of the football field between each end zone and each sideline with 1 foot of water on it. Okay, a football field is about an acre. And if you could fill that up with 1 foot of water, that would be the volume of 1 acre foot. So we're looking at, you know, a third to half of an acre foot over each one of these grid cells. Now that doesn't tell us the total volume of water that was on polygon 2. It just doesn't do that for us. So how could we do that? Well, we need to like add up, excuse me, add up the value of each one of these cells, the volume associated with each one of these cells. So how could we do that? Here's another tool for us that we will use again, zonal statistics. What zonal statistics does is it'll compute values based off of a raster. It returns that as a polygon, so a vector data type. So let's just try it and see what we put in. If we put in raster calc, so I'm just going to put in for this input raster or feature zone data. This is the data set that defines the zones. So what that means is we probably could have done this without cutting out our raster, which is kind of cool. We'll try that on polygon number 1 or 3. And just, well, we'll try it again on polygon 2, see if it works. But we're gonna look at the raster calculator values that we computed. We're going to output a new raster. We're going to call it zonal. I'll call it zonal stats. And I'm just going to say P2 for polygon 2. And what do we want on this? We could take the average. We could take the max, the min, the range, standard deviation. We'll take the sum. Okay. And so we're going to say OK and see what it produces as we add up all of the values in this cell. I close that out, and what does it tell us? Well, it says that there's going to be 1.2 million acre feet of water, okay, or 1.2 times 10 to the 6th. That's what that E plus 006 means. So 1.2 times 10 to the 6th volume of water, acre feet of water, that will fall over this area based off of our rainfall information. That's a lot of water, and I'll tell you, that's a big area, so I hope they get that much. They definitely need it. So that was kind of cool. Let's and that gives us our solution. Okay, let's try that really quickly. I'm not exactly sure what this is going to do. But let's go ahead and we're going to use raster calculator one more time and do it over the entire area of Utah. And then we'll try zonal stats and ask it to just pick out polygon 2 and see if we get the same number. I think that would be pretty interesting to try, and I think we'll learn something together as we do it. So I'm going to quickly grab raster calculator. Okay, and this time we'll take Utah Central precip, and we're going to multiply by 100 times 100 divided by 12 divided by 43,560, and we'll call this raster calc UT precip, and let's have it compute for the entire the entire area of interest. This could save us a little bit of time. Okay, and it does that easily. Now let's try another zonal stats and see if we could skip the extract by mask. Zonal statistics. I guess you can't put in abbreviated values to search. And let's try Polygon 2. That'll give us some data to compare against. And input value raster, we'll say raster calc Utah precip. We want the sum. And we'll say, okay, let's see if it grabs the same numbers or at least gets quite close. And hey, looky there, it does. Okay, so for Polygon 2, it computes it the same. We could have skipped using extract by mask. I'll tell you, extract by mask is still a good tool for us to learn. Now let's go ahead, let's do that one more time. Let's try polygon number 1. Polygon 1 will be kind of interesting because it has two zones. So let's see if it computes those separately or together. Okay, it computes those together. So as you look at this, it didn't quite get to 1 million. It's 950,000. Okay, was the total volume over that shape. That's pretty cool. We were able to do that and save an operation on the extract by mask. I hope one of the takeaways from today's discussion that comes out crystal clear is how important it is to consider the dimensions of our cell size. Okay, where did they fall? Where did it result at? What did we need to do to make it so those dimensions or units were appropriate and adequate for our study, which in this case was to project the raster into a different coordinate system. So that was one thing. We did just a little bit of math on the raster. Now, I don't know if you've done that before. Take raster values, multiply them by something, divide them by something. It does it cell by cell, and it's pretty cool that we can do that. It really makes raster data valuable, and raster data will never go away for that very reason, that we can have continuous information spread out over some region. So keep that in mind as you think about what we did today and as you work on and complete this project. We will continue a discussion about this project on this next Friday. Okay, so a week from now we'll have another video posted to help us wrap it up. And then 2 weeks from now we will start another project. Okay, so on February 2nd, right before this is due, we'll introduce our next project and where we're headed with that portion of the class. Thank you for tuning in. I hope you have a great day. Please let me know if you have any questions. Thank you.